We are so familiar with objects made of metal being part of our everyday lives that we rarely, if ever, pause to think about where metals come from, or that they come from anywhere at all. The reality is that we get metals from rocks. Very few rocks look anything like metals, so there's obviously quite a bit involved in turning a pile of rocks into metal. Different rocks contain different chemical compounds, so we have to choose the right type of rock to get whatever metal we want. We call a rock which contains enough of a metal compound for it to be worth extracting an ore. High-grade ores contain lots of the metal compound we're interested in, while low-grade ores contain rather less and may cost more to process than the metal is worth. There is a finite supply of all ores. Once we've removed them from the Earth's crust, they are gone and will never be replaced. We say they are non-renewable, so recycling metals is very important. In rocks, the metals are chemically combined with other elements which have to be removed. This is done using a variety of different chemical processes, depending on what elements need to be removed to leave the metal behind. One of the main ores from which we obtain iron is called hematite. Hematite is mainly iron oxide, so we need a chemical means of removing the oxygen in order to obtain iron that we can use. Only the most unreactive metals are formed in the Earth's crust in their metallic form, and not combined with other elements. Gold is one example, and in some places small amounts of silver metal can be found. We call these native metals.
Here, a very, very small gold nugget. This is from Australia. If you look very carefully, it's all sort of rather interesting shapes. It's sort of knotted and curled and so on. This is because there would have been mineral in here, would have been some rock in here, and this has been dissolved away in acid to leave the pure gold. Gold is so unreactive, you can actually just find it occurring native like this as pure gold. You can find lumps of this if you're lucky. But most of the other metals are more reactive, and over time they react with the oxygen, they could react with water and so on, and form different minerals. And these are how we would normally find our metals, locked up in minerals. Here's a metal that you can sometimes find, if you're lucky, in the native pure state. This is copper. So I have some copper here, and here's the rock that it can be found in. So there's a stream of copper here. Can occur native sometimes, but more usually it occurs as a mineral. And here is a copper mineral, this beautiful green mineral here, called malachite. This one is actually being polished. This is how it would come out the ground normally, sort of slightly dull colour, but polish it up and you get this fantastic green here. So this is, well, a form of copper carbonate. This is malachite. Okay. Now the question is, how can we get the copper out of these ores? Now I have some beautiful little malachite carvings here, some animals. We have, there's a dog, there's, well, a dog's head actually, the rest of him sort of had an accident. We have a frog, a lion, a little bird and a cat. So we're going to do a little experiment on one of these to see if we can get the copper out of the malachite here. Oh, good. I can relax now. Right. Well, let's take the dog's head, mainly because my mum quite likes the other ones and she wanted one of those. But anyway, so let's take Chip here, and we're going to heat him up. Now, take Chip, and at the moment he's this lovely green colour, but if I heat him up in the Bunsen here, the copper carbonate that he's made of is going to decompose, and it gives out carbon dioxide gas and forms copper oxide. And the copper oxide, we'll know when we're beginning to get some copper oxide because the copper oxide is black. Okay? So actually already you can see that the bottom of the malachite here, we're getting a black coloration, and this is as the carbonate is decomposing and forming copper oxide. And we can look at the equation for this. So here we have the equation, copper carbonate plus heat forms copper oxide and carbon dioxide gas. Right, well I'm going to heat him up a little bit more strongly over here on a piece of charcoal. Remember, the charcoal is impure carbon. Right, so let's just heat him up strongly. So he's decomposing. and forming, oops, there goes a bit of him, forming copper oxide. So he's certainly very black now. But the copper oxide is going to, well, it begins to react with the carbon in the charcoal, and the carbon steals away the oxygen from the copper oxide, forming carbon dioxide, leaving behind the copper. And this is the, well, essentially the process that's used to make many metals. You heat up the metals with some carbon, and the carbon steals away the oxygen from the ores, leaving the metal behind. I think I'm doing quite nicely. We're beginning to get some molten copper forming. All right, let's see if I can pick up this with the tongs. Okay, thank you. And put this into some water here, just to cool it down. And if I pick out the lump that we've just made here, actually there's a nice bit in here I can see. Yep, you can see the reddish colour here of, well, the copper metal. Okay, so we've actually converted, well, first of all, the copper carbonate, the natural mineral, the malachite, into copper oxide by driving out the carbon dioxide, leaving copper oxide, the black colour, and then the oxygen has been stolen away from that using the charcoal here from the carbon, stealing away the oxygen to reveal the copper. And these are some lumps that we made in the earlier lectures. So copper metal. And of course, copper was the first metal that was chemically prepared. After the Stone Age, when people were using stone tools, flints as axes and spearheads and so on, after that came the Bronze Age or the Copper Age. And this was because copper was one of the easiest elements to actually obtain. It's much easier to make than iron. So after the Bronze Age came the Iron Age, when they had higher temperatures available to make iron from iron oxide. But here we're making some copper. Here is the reaction there for the copper oxide, having its oxygen taken away by the carbon to form carbon dioxide, but leaving the copper behind.
There are three common types of metal compounds found in ores, and a different chemical processing is required to obtain the metal from each type of compound. Some ores contain metal carbonates, where the metal is combined with carbon and oxygen. Malachite is a copper ore of this kind. Other ores contain metal combined with only sulphur. These are sulfide ores, and galena is lead ore, a common example. Fool's gold, which contains no gold at all but is a compound of iron and sulphur, is another sulfide ore. We've already met hematite as an example of an ore containing a metal combined only with oxygen. Aluminium ore, called bauxite, is another example of an oxide ore. The first stage in processing an ore containing metal carbonate or metal sulfide is to turn it into a metal oxide. Once this has been done, we can treat them in the same way as other ores containing metal oxides. The way this is done is by roasting the ore, which involves heating it strongly until it reacts. While the process is the same for carbonates and sulfides, the chemistry that takes place is different. Carbonates react when heated strongly by giving off carbon dioxide gas, leaving the solid metal oxide behind. This is called thermal decomposition. In general, if we heat a metal carbonate, it will form a metal oxide plus carbon dioxide. For example, if we roast malachite, which contains green copper carbonate, we will get carbon dioxide given off and black copper oxide left behind. When a metal sulfide is heated, it will react with the oxygen in the air, giving off sulfur dioxide gas and leaving the solid metal oxide behind. Air containing oxygen is needed when roasting sulfide ores, while it's not needed for thermally decomposing carbonate ores. For example, when we roast the ore sphalerite, which contains zinc sulfide, it reacts with oxygen, forming zinc oxide and sulfur dioxide. Balancing the equation shows that we need 3 oxygen molecules to react with every 2 zinc sulfides, and that we will get 2 molecules of sulfur dioxide and 2 zinc oxides produced. Make sure that you understand how this equation was balanced and how to balance equations like this. Once we have a metal oxide, we finally need to remove the oxygen to leave the metal behind. This is done by a process called reduction, but exactly how to reduce the metal oxide to a metal depends on how reactive the metal is. Here we can see the reactivity series of the metals, with the most reactive metals at the top of the ladder and the least reactive ones at the bottom. To remove the oxygen, we need to react the metal oxide with something more reactive, which will steal the oxygen from the metal and bond with it itself. We could simply use a more reactive metal than the one that we want to extract, but that would be wasteful as metals are finite resources. Carbon is cheap and plentiful and can be used to remove the oxygen from metals less reactive than carbon. The reactivity of carbon compared to the metals is also shown. Any metal below carbon in the reactivity series could be obtained by reducing its metal oxide using carbon. The carbon reacts with the oxygen in the metal oxide to form carbon dioxide, leaving the metal behind. If the metal is more reactive than carbon, we can use electrical energy to split up the metal from the oxygen in a process called electrolysis. From about 1750 to 1850, Britain was the world's leading producer of lead, which was used for roofing, piping, glazing, and as a component in some paints. Lead ore was dug out of mines and crushed before roasting it to turn the lead sulfide into lead oxide. The chemical formula for lead sulfide and lead oxide are shown. Pause the video and work out what the lead sulfide reacts with and what the other product would be. Note down the chemical formulae and balance the equation. Here's what you should have written. Once the miners had made lead oxide, they had to reduce it to lead. They knew that lead was less reactive than carbon, so they heated the lead oxide with carbon, making carbon dioxide gas and leaving the shiny metallic lead behind, which was poured into moulds to form lead ingots. The equation for the reduction is shown, but it's not balanced. Pause the video again and see if you can balance the equation. Reduction doesn't always have to be carried out using carbon, however. Any more reactive metal will be able to remove the oxygen and leave behind the metal we want. Iron is more reactive than copper, and scrap iron is sufficiently cheap and plentiful that it can be used in making copper from copper ores instead of carbon, for example. One of the most widely used metals is aluminium. Fortunately, aluminium ore is very abundant, which means there is a lot of it and it won't be running out anytime soon. Bauxite, which is aluminium oxide, cannot be reduced using carbon because aluminium is more reactive than carbon. In principle, a more reactive metal than aluminium could be used, but these are expensive and finite resources themselves. It is more practical to use electrolysis, and this is done industrially. The aluminium ore is melted at a high temperature, then an electrical current is passed through it to separate the aluminium from the oxygen. The equation shows how aluminium oxide is turned into aluminium metal and oxygen gas. Pause the video and see if you can balance the equation. Of course, melting crushed rocks requires a lot of expensive heat energy, and the amount of electrical energy needed is very high too, so electrolysis is a costly process. We have already noted that ores are finite resources. Some, like copper, have already almost run out, and only the low-grade ores containing small amounts of copper compounds remain. The only copper we will have in the future is that which we can obtain from those low-grade ores, and that which we recycle, which is why copper is expensive, and copper scrap has a high value. Scientists are working on processes to obtain copper from these low-grade ores. Of course, because there isn't so much copper in them, the processes have to be as inexpensive as possible, and scientists have turned to biological methods. Some plants are very good at extracting metals from the soil through their roots and storing them in the plant tissue. A method called phytomining has been developed to make use of these plants. Bacteria too can be used. Bacteria feed on the metal compounds in ores, producing a solution which contains the metal from the ore, which can then be concentrated, ready for the metal to be extracted by electrolysis. This process is called bioleaching. Here's a short video clip explaining how phytomining and bioleaching work.